So we are into now new lecture. So what we will do is that first we will review the last lecture and then we will go through the new concepts. So in the last lecture we started our analytical solution to the polarizability of dielectric materials, and in this first we took electronic polarization, and there we looked at the effect of electric field on the electron cloud around the nucleus and shifting of centers of charges, which gives rise to what is called as electronic polarization. And then how do you work out the polarizability? You calculate the forces due to electric field and the opposing force, which will be Coulombic force, and equate these two forces to find out what is the equilibrium separation, what is the equilibrium distance, and this gives rise to the dipole moment, and from that we can find out what is electronic polarizability. And the conclusion that we drew from this exercise was, as for larger the atom is, larger the polarizability is. So larger atoms can be polarized more than smaller atoms can be, and this is also seen as a difference in anions and cations, because anions typically tend to have larger radius as compared to cations. So for example, you see in case of fluorine, chlorine, bromine, iodine, as the size of the ion is going to increase, the alpha value, which is the polarizability value, also increases. And similarly for cations, as we go from lithium to sodium to potassium, the value of polarizability also increases. However, if you compare these are your anions and these are your cations. So if you compare and that too, these are alkali cations. So if you compare these alkali cations with these halogens, you can see that polarizability in case of cations is much more smaller, and this is again typically due to size of the smaller size of the cations. Now the next thing that we discussed was ionic polarizability. Now this arises from what we learned earlier was ionic polarization. So we know what ionic polarization is. We just took a case of sodium chloride, and when the field is 0, then all the atoms are sitting in their, all the ions are sitting in their equilibrium positions. As a result, whatever dipole moment components are there, they cancel each other because of symmetry of the lattice, and hence the net dipole moment is equal to 0. When we apply field, then there is a relative displacement of ions with respect to each other. So for instance, in this schematic diagram, the cations are all shifted towards right, which means they are closer to their right anion neighbor as compared to their left anion neighbor. So as a result, the distance between cation and anion on the one side is different as compared to distance on the other side, and this results in net dipole moment. Excuse me, it's not magnetic, it's just electric dipole moment, and this is finite, and this happens when you apply electric field. So again we did the force balance. So the force which is due to electric field is QE, and then the restoring force is KD, which is if you consider these bond between the ions as a spring. So based on that, we found out what is the separation, what is the displacement D, and this displacement D is given as QE divided by YD naught, and from this you can work out what the dipole moment is, and then this gives you ionic polarizability alpha ionic, which is Q square divided by YD naught. So what this expression tells you is that larger is Y, and Y is Young's modulus. Larger the Young's modulus is, smaller the polarizability is. Similarly, larger the D naught is, smaller the polarizability is, which means a bigger unit cell where separation between ions is much larger, there will be far less polarization, and the more important thing is Y, and this Y is Young's modulus, which is, and Young's modulus, higher or lower Young's modulus is because of fundamental reasons such as bond strength. So higher the bond strength is, higher the modulus is, and less the polarizability is. So what it means is that the materials which have higher modulus or high stiffness, higher bond strength or higher melting point materials, they tend to have lower polarizability as compared to the ones with lower modulus, and this is true for of course the ionic systems where you have a group of cations and anions, and mostly in case of symmetric lattices. So when you look at some of the examples are we can calculate we can work out the values of dielectric constant for variety of materials. So what I have taken here is a group of cadmium zinc based materials and cadmium based materials. So zinc oxide, zinc sulphide, zinc selenide. So as you go from zinc oxide to selenide, the bond strength increases decreases, as a result the modulus and the melting point decrease, as a result the polarizability increases, and as a result your dielectric constant increases, and same is true about cadmium sulphide and cadmium selenide. So these two parts have given you some idea about the electronic and ionic polarization. So what we are now going to take up is what is called as dipolar polarization, the third part of the polarization. So this is let me just see which lecture was last one. So last one was 18th, so this would be 19th lecture. So here what we will start is dipolar polarizability. Now dipolar polarizability happens when there are dipoles which are present and they are present independent of each other, which means material has a permanent dipole moment. So for instance, I can give you example of, let's say, so this is hydrogen, oxygen. So this is naturally water molecule. So you have a component so you have basically two components, and these two components will have a net dipole moment going in from this direction. So this is positive, this is positive, this is negative. So you have a component in this direction, component in that direction, vertical components cancel each other. So as a result you have a finite mu net for this molecule. Now each of these molecule, what it means is that has a dipole moment. So what we say, permanent dipole moment, and these materials are called as polar materials. So for instance, a water molecule has a permanent dipole moment, and as a result it will have it will be called as polar material. On the other hand, if you take example like methane is CH4. So here in this case all the dipole moments components cancel each other. That means mu net is equal to 0. So a symmetric molecule like methane will not have a dipole moment, but a asymmetric molecule like water will have a dipole moment, and that is why materials having permanent dipole moment are called as polar materials, and materials which don't have a permanent dipole moment, they are called as non-polar materials. So this is just a definition which you must remember. Now what happens is that in water, in case of water for example, so you have many of these water molecules. Now in case of water molecules, each molecule's orientation is independent of each other because of high thermal energy at room temperature. So the thermal energy prevents any kind of alignment. So what you have here is so basically what we have is random molecules due to kT. So at a finite temperature T, all these molecules have sufficient energy to randomize their orientation with respect to each other. So when you have such a situation, so given the fact that each of these molecules will have mu, now since these, now what this will look like is all the mu's are in various different directions. So what the picture looks like is as if you have mu's present in all the directions. If you have mu's present in all the direction, then mu net for such a system will be equal to 0, and this happens when temperature is finite, typically room temperature, and electric field is equal to 0. So in the absence of any electric field and at a finite enough temperature, all these water molecules are randomly located with respect to each other, and because of this randomization assisted by the thermal energy that is present leads to a picture in which all the dipole moments are randomly distributed. As a result, mu net is equal to 0. So despite having a permanent dipole moment, a molecule like water does not give rise to any dipole moment, any appreciable dipole moment in the absence of electric field. When you apply electric field, then what happens? When you apply electric field, then the picture changes, and what happens is that schematically all these molecules which are present, they tend to align with the direction of applied field. So the picture changes a little bit now. The picture changes in such a manner. So I am not going to draw the molecule. So let us say the previous picture was like this. So each molecule is represented by each of these arrows. So this is the, so green one is when E is equal to 0. Now what I do is that I apply electric field. Let us say electric field is applied in this direction. So what happens is that these new, so this application of electric field tends to rotate these dipole moments in that direction. Now this rotation depends upon the strength of the field. Typically it is not complete, but it is sufficient enough to give rise to what is called as a permanent finite dipole moment. So for instance, if the direction of field is this will become like this is anyway, so this will tend to become like that, this will tend to become like that. So all of them will tend to orient themselves slightly along the applied field. So if this has happened, which means there is a net tendency of dipoles to align in the direction of applied field. As a result, what happens is that this mu net is not equal to 0, and which means this gives rise to a finite dipole moment, and then this gives rise to polarization, and this results in large enough epsilon r. Now what you will see in many books is many books show complete alignment in the direction of applied field. That is not necessarily true, because if all the water molecules were completely aligned in the direction of applied field, then the dipole moment or the dielectric constant that you would observe will be huge. But what we see practically is epsilon r of the order of 80, which is large, but it is not huge. So what it basically suggests that there is alignment, but that is not complete alignment in the direction of applied field. So but whatever is given in the books is a schematic diagram. It is just for the sake of illustration. So don't take it literally as if all the molecules are going to align in the direction of applied field. So this essentially highlights that orientation of all the dipoles is just a bit shifted towards the direction of applied field, leading to basically an average non-zero dipole moment in the direction of applied field. Okay. So now thermodynamically speaking, what we need to do if such a situation is stable, then this must have a minimum free energy, and what do you need for to calculate free energy, to calculate the free energy, you need something called as internal energy, and then you need something called as entropy. So because you know that for any stable system, delta G must be negative, and what is G meant, where delta G is nothing but your Gibbs free energy, and G is composed of two terms, H minus Ts, where H is enthalpy, which is built up of a component of internal energy. So H represents internal energy and S is entropy. So these two factors have to be taken into account in order to calculate what is delta G. So we must know what is delta S and we must know what is delta H. So for this, now as we are saying that all the dipoles are not completely aligned, some of them are aligned, some of them are slightly at certain angle, which means we have a scenario. So what we have is basically we start with a picture like this, a schematic. So you take a charged dipole like this, apply an electric field E, which means you will have a mu, and this angle, let us say, is theta. Okay. So if this angle is, so this is general picture. So theta will vary from minus 90 to plus 90, because all these dipoles will be, so you can have dipoles going from, since you have dipoles going from all the way from so you have dipoles going all the way from, let us say this is theta. So theta goes from plus 90 degree to minus 90 degree, or plus pi by 2 to minus pi by 2, or minus pi by 2 to plus pi by 2. But since you have net slight tendency of dipoles to align in the direction of applied field, as a result you will have a net number of dipoles which are finitely aligned, or net number of dipoles aligning with the applied field, giving rise to a net dipole moment, and that we will calculate in a while. So this is the picture. So schematic diagram is you have a charged dipole which is aligned at an angle theta with respect to the applied field, with the dipole moment vector as mu. So the internal energy, let us say, so the internal energy is, let us say, U, and this U is nothing but, U depends upon the orientation of this charged dipole with respect to the applied field. So U is nothing but a function of this theta, and this U can be written as minus of mu dot E, or mu E cos theta. Okay. So you can see naturally when theta is equal to 0, what it means is that complete alignment. And this means U is equal to minus mu E, which means minimum energy. And when you have theta is equal to 180 degree, then you have complete misalignment, or both are out of phase, and then U becomes plus mu E. So you understand the sign of this significance of the sign minus. The sign minus represents basically the reduction in the energy of the internal energy of the dipole when it aligns completely with the applied electric field. So U will vary from minus plus mu E to minus mu E as it goes from theta is equal to 180 degrees to 0 degrees. So it depends how you take it. You can take minus pi by 2 to plus pi by 2, or you can take from in this case we are measuring. So let me just make a correction there, because I told you. So we are measuring theta from here. So what basically it means is that let me just make a correction here. This would mean 0 to 180. So theta is increasing in this direction, So closer to, so if this is the E, then closer to E is equal to 0 and further away from E will be 180. So it means the same, but just for the sake of clarity, let us take 0 to 180 instead of minus pi by 2 to plus pi by 2. So now we can work out what internal energy is. So this u theta, as we know, is equal to minus of mu e cos theta, and we can take the mod of these in a just to take the scalar values of these. So what it means is that you have, since you have many more thetas available, what you will have is, this is the applied field, right, and then you have one dipole like that at theta, another dipole like that at theta, and you might have several dipoles. So if you have, so you can have this is the applied field, and around the applied field you will have all these dipoles making an angle theta. So what this makes is a kind of cone around. So all the dipoles which are oriented at an angle theta with respect to applied field E will make a cone which has an apex angle of theta, or apex angle of 2 theta. Similarly, you will have some other dipole moments. So this is, let us say, theta 1. You will have some other dipole which are making an angle theta 2. So they will make another. So this will be theta 2. You might have something in this direction as well. So theta 3. So what basically I am coming to is, now in order to calculate the net dipole moment along E, you will have to integrate this overall energy with respect to theta in order to find out total dipole moment. But before we do that, we need to find out what is the net number of dipoles which are aligned in the direction of E. Then only we would be able to find what is the net dipole moment. So in order to do that, we need to first calculate. So we need two quantities. One is number of dipoles, and then we need the dipole moment component. And then we need to multiply these two in order to get a complete picture. So now, in order to get, first of all, minimize the free energy, we said we need entropy, we need internal energy. We know what internal energy is, but we don't know what entropy is, and to calculate the entropy of the system is mathematically not very easy. So what gives us a respite is what is called as Boltzmann approximation. So what we are saying is, using the Boltzmann approximation gives us a number n, let us say n number of dipoles having energy u of dipoles making angle theta, and that is given by as that is proportional to exponential of minus u by kt. So that simplifies our life. So basically, if you have scenario like this, so this is E and this is the dipole moment mu, this is angle theta for this cone. So what I am saying is that, using Boltzmann statistics, I can calculate number of dipoles at angle theta having energy u theta. This can be given as n u theta is equal to exponential of minus of u theta divided by, or proportional to exponential divided by kbt. So this makes sense. This is nothing but Boltzmann statistics. Okay. So what n u theta would mean, or we can say this just as n, and this n theta would be equal to a constant exponential minus of u theta divided by KBT, where KT is nothing but Boltzmann constant. Okay, and you can find the value of this constant in any book. So now what we can do is that we can calculate the component of dipole moment parallel to the applied field. The component of so what we can remake this picture now as so this is the direction of applied field. So I'll just turn it 90 degrees on the counterclockwise. So this is your this is E, this is one cone. We might have another cone, okay, and these are lying on the so this basically looks like as if it's a sphere. Hang on. So what basically we draw it as a sphere. Let us say this is the direction of applied field E. So the first cone, let us say, is this. Another cone can be this, all right, and so what we are interested in basically. Okay, so let us say this angle is theta and this angle is d theta. Okay, so this is a picture that so this is a spherical representation of dipoles. So what we want to basically calculate is the dipole moment. So parallel to applied field. Okay, for that we need the solid angle d omega, which is so this is the segment. So this is the segment, let us say dA prime or dA, just dA, let's say. So first we need the quantity, and this dA will subtend a solid angle on this part. So solid angle d omega, and within the segment theta to d theta. So solid angle subtended by dA within the segment theta to theta plus d theta. So this is up to theta, and then you have d theta. So you have a segment of, so what we are interested in, number of dipoles lying between this segment theta to d theta. So what is this number of dipoles? So number of dipoles between theta and theta plus d theta will be equal to, you have n u theta, which we calculated using Boltzmann statistics at any given theta, multiplied by d omega, okay, where d omega is the solid angle, and the total dipole moment will be nothing but sum of all components of mu e, mu, all components of mu along E. So basically sigma mu, all right. So this mu E, which is in the direction of applied field, will be equal to number of dipoles within that segment multiplied by what is, so if we go back to previous picture, if let us say each of these has value mu, then this will be mu cos theta, right. So now what we need to do is that we need to, so this is within for that segment. Now we need to now what we can see is that we can vary the theta from 0 to 180 degree, and if we vary the theta from 0 to 180 degree, if we want to calculate for all the dipoles which are in this region, then we need to integrate it from 0 to 180 degrees or 180 degrees to 0. So what we need to do is that, so the total dipole moment would be from 0 to pi n u theta mu cos theta. So this would be 2 into, because we are taking on the both sides, so 2 into n u theta mu cos theta into d omega, and number of dipoles would be 0 to pi n, sorry, we do not need to take 2 because this 2 is already included in the number of dipoles, because we are taking all the dipoles which are forming that cone. So this n u theta into d omega. So if I now, so this is mu total. So if I divide mu total by number of dipoles, which is n, this gives me, so mu total divided by n gives me average dipole moment. So this mu average is 0 to pi n u theta into mu cos theta d omega divided by 0 to pi n u theta into d omega. Now we need to find out what is d omega. D omega is solid angle, and by definition solid angle for this unit area dA would be equal to dA divided by r square. And as you can see, so in this sphere you have a sphere, so you basically are interested in this strip of thickness d theta, and this is the radius of sphere. So if this is, so basically this is theta, if this is r, then the area of this strip, which is this shaded strip, so if you this would be equal to r sin theta into, so this would be basically r sin theta, okay, into 2 pi r d theta divided by r square. So r will cancel each other. What you will have is 2 pi sin theta d theta. So basically what I am going to do is that you are just taking a segment of the sphere. So if you just open it up, this will open up like this. So this will be the segment, okay. Now this distance is r sin theta. So what you will have is, so if this is r sin theta, you have a circle of radius r sin theta. So the length would be 2 pi r sin theta. So this would be equal to 2 pi r sin theta, whereas this would be r d theta. So if you multiply these two together, what you get is r sin theta, I should have taken 2 pi r sin theta into r d theta, okay. So I'll just modify this for the sake of clarity. This would be 2 pi r sin theta into r d theta divided by r square. So, these cancel each other. So, what you have is 2 pi sin theta d theta. So, now you have got a magnitude of d omega. Okay. So, if you now put the value of d omega, what you get is, so mu, average mu is equal to mu coming out of it. So, this is 0 to pi sin theta cos theta. So, you just have to replace for d omega into exponential of mu e cos theta by kt or kbt into d theta divided by 0 to pi sin theta exponential of mu e cos theta divided by kbt d theta. So, we have zeroed down to this expression for average dipole moment, which is due to all these dipole moments which are at some angle theta around the applied electric field, and since they have a natural tendency to incline in the direction of applied field. So, there are always some, so there is a net finite dipole moment and this is average. So, what we have done is we have calculated total finite dipole moment divided by the number of dipoles, and this gives rise to average thing. Now, in order to solve this equation, we take this mu e divided by kt is equal to what is beta. So, suppose and cos theta as equal to x. So, when you substitute in this equation, so supposing mu e by kt is equal to beta and cos theta is equal to x, and if you substitute in the previous equation, you get the expression for average mu, which is mu. So, if you change cos theta from 0 to pi, theta from 0 to pi, then naturally x will vary from +1 to -1, because if theta was equal to 0 degree, cos theta will be equal to 1, theta would be equal to pi, cos theta or x is equal to cos theta would be equal to -1. So, +1 to -1 x exponential of beta x dx divided by +1 to -1 exponential of beta x dx, and this is called as, and this whole thing which is there in this body, this is called as L beta or Langevin function. So, this mu becomes, average mu becomes equal to mu L beta. So, now this gives rise to what is called as a finite value of average mu. So, this Langevin function L beta is defined as cot of hyperbolic beta minus 1 by beta. So, we are not going into theory of Langevin function, but basically this function is so you know cot of hyperbolic x, which is nothing but cos of hyperbolic x divided by sine of hyperbolic x. So, which you can represent in exponential functions of x. So, we are not going into details of this, but the values of Lx vary between, so this L beta will vary between 0 to 1. Okay. So, when you plot this L versus beta, so if this is 1, if this is 0, then it varies something like like that, and this, the slope at lower values of beta, which gives rise to what is called as asymptotic value, this is 1 by 3. This L beta will give rise to what you can say is nothing but, it will in the end signifies what is the dipole moment. So, and what is beta? Beta is nothing but mu e by kT. So, what it tells you is that effect of temperature, right. So, higher values of beta would mean lower temperatures, and lower values of beta on the contrary would mean higher temperatures. So, this gives rise to as an effect of temperature. So, for large values of beta, what this would imply? This would imply large field, as you can see that mu e by kT. So, larger the E is, larger the beta is, or low temperature. And what that would basically mean is that larger the temperature is, lower the larger the field is, lower the temperature is, this situation would tend to align all the dipoles in the direction of applied field, because lower temperature would mean lower thermal vibrations, as a result lower thermal randomization. So, tendency to align in the direction of applied field will increase, and if you have large enough field to align all the dipoles, that would mean all the dipoles would align. So, intuitively if that means that is true, then L beta will become equal to 1. So, average mu in such a situation would be equal to mu. So, which means what it means is that all the dipoles are aligned. So, average dipole moment for each dipole would be equal to mu. So, that is fantastic. So, this is theoretically correct, and for small values of beta, but this situation is something which is not practically feasible. So, L beta is not 1 is equal to 1 is not practically achievable, because large enough field we are talking of very high fields, and low temperature means temperature closer to 0 K. So, so practically unfeasible. So, on the contrary, small values of beta, which means beta is smaller than 1, what that would mean is normal field. So, normal magnitude of field that we encounter in devices, and moderate temperatures, moderate or high temperatures closer to room temperature, etc. And so, for beta closer to 0, this slope becomes, as I said, is equal to 1 by 3, and as a result this L beta for a smaller values is given as 1 by 3 beta, and this is what we use for the calculation of average mu. And this is generally true, because in practical situations for normal fields and moderate temperatures, beta tends to be much smaller than 1, much more closer to 0. As a result, this L beta is equal to 1 by 3 beta is a correct kind of approximation. So, if you now substitute this, what you get is average mu becomes equal to mu e by kT 1 by 3, this is the beta, into mu. So, what it gives you is that mu square E divided by 3 kBT, let us include kB. So, what is alpha from here? So, alpha D, which is dipolar, is nothing but this, because mu is equal to alpha E. So, alpha becomes mu square divided by 3 kBT. So, this is a fantastic expression, because now for the first time you see that the polarizability of a material is dependent on temperature. In the previous cases we did not see that. So, electronic and ionic polarizabilities were independent of temperature, but what we see here is as the temperature increases, the polarizability goes down, and which is true, because as the temperature increases, the randomization would increase and material would, so the net polarization would tend to go down. So this equation holds pretty well for large enough temperatures or moderate temperatures and moderate and nominal values of, sorry, what did I do? I rubbed it. The nominal values of field. This alpha, so this is the expression for dipolar polarizability. So, what essentially now we have established is, we have established a mechanism to look at the polarizability of polar materials, which give rise to a fundamental phenomena, very important phenomena called as dipolar polarization. And the polarizability, this we have worked out, is worked out at a condition when fields are nominal and temperatures reasonably high. When the temperatures are very close to 0 Kelvin or the fields are very high, so that all the dipoles can be aligned, in that case the average dipole moment will be equal to nothing but dipole moment of each of the dipole or theoretical dipole moment. So, so basically this establishes this. So far we have established mathematical or sort of analytical treatment of three polarizabilities. We looked at electronic polarizability, which is dependent upon the size of the atom and which is present for all the materials, because all the materials will have atoms. Then you have ionic polarizability. Ionic polarizability is true for ionic solids, symmetric ionic solids, and then of course symmetric, non-symmetric both, as long as you have ions of different types. And then of course you have dipolar polarizability, which is there for dipole, which is there for materials which have dipole moment, and these dipole moments tend to be randomly distributed with respect to each other in the absence of in the absence of applied field. But when you apply a finite amount of field, these dipole moments tend to align in the direction of applied field, and this gives rise to what is called as the finite magnetic dipole moment. I keep on saying magnetic, it's electric dipole moment. And then we looked at the formalism. We said that if all the dipoles, if the dipoles in various places of the crystal making different angles, so let us say this angle was theta, so you will have cones of different angles, different thetas with respect to applied field. And then what you are interested in calculating the number of dipoles at any angle theta, and the energy with having energy u theta, which is coming from Maxwell-Boltzmann statistics. And then we integrate these in order to find out the total number of dipoles. You need to integrate from 0 to pi, and in order to find out the total dipole moment, you need to multiply the component of dipole moment parallel to electric field multiplied by the total number of dipole. So when you take the ratio of these two, what gives rise to the average dipole moment. And then we looked into Langevin function and looked at how it gives rise to what we have arrived to the expression of alpha d, which is the dipolar polarizability, which is a very important expression because it, for the first time we have encountered the temperature dependence. So this is a very important outcome whose repercussions will be much more clear as we go on discussing more about polar materials. So we'll finish here today. In the next class, what we will take is so far we have not looked at the effect of frequency in quantitative way. So we'll look at the effect of frequency or alternating electric field on the behavior of dielectrics, so which is very important from the point of view of applications. And there we come in contact with some fundamental quantities, and we'll see that this dielectric constant, which we are saying epsilon r at the moment, it will have a real part, it will have an imaginary part, and then we will also learn about quantities such as loss factor, etc. So we will finish here. In the next class we will take up these topics. Thank you.